Every AI product you've touched lately, the chatbot that knows your company's docs, the Find Similar button, the recommendation feed, sits on the same piece of infrastructure, a vector database. And in the interview, the second you say, "I'll store the embeddings and search them," a good interviewer leans in with the question that separates people who've used one from people who've built one. How does it actually find the nearest vectors? Here's the naive answer, and why it's a trap. You have 10 million vectors. A query arrives. Compare it to all 10 million. Keep the closest. That's brute force, and it is perfectly correct. It's also dead on arrival, because comparing against every vector is order n. And at a billion vectors with a 50 millisecond budget, you'd need a small data center for a single query. So here is the secret that defines this entire category of database. It gives up on being correct. A vector database does not find the true nearest neighbor. It finds a very close one, 95 to 99% of the time, while looking at a tiny fraction of your data. It trades a perfect answer for a fast one, on purpose. And once you accept that one trade, everything else, HNSW, quantization, DiskANN, is just a different way of making that same trade under one relentless pressure. The good indexes want to live in memory, and memory is expensive. Get that, and you can design vector search at any scale. Miss it, and you'll propose a for loop over a billion vectors and lose the room in 30 seconds. Let's frame it before we build. Functionally, a vector database does four things, and juniors only name the first. 1. Top k nearest neighbor search. Given a query vector, return the k closest stored vectors by some distance. 2. Filtered search. The same, but constrained by metadata, closest that this user can see. And hold that thought, because it's the secretly hard part. 3. Writes, insert, update, and delete vectors continuously, with new data searchable within seconds. 4. Persistence and durability. This is a database, not a cache. It can't lose your data. Clarifying questions that signal seniority, and you should ask them before drawing anything. What's the scale? A few million vectors or billions? What's the recall target? Do we need 99%? Or is 95 fine? Because that one number moves the whole design. What's the latency budget? 10 milliseconds or 100? What's the read-write mix? A static index rebuilt nightly or a fire hose of live updates? And what are the dimensions? Because that drives memory and cost directly. Then, the non-functional reality you say out loud early. The system is approximate by design, so recall is a tunable dial, not a guarantee. And the dominant cost is memory, because the fast indexes want to sit in RAM. A useful capacity instinct. A single vector is dimensions times 4 bytes. A 1500 dimension vector is about 6 kilobytes. So 100 million of them is over half a terabyte of raw floats before any index overhead. That number, said early, is why half this video is about not keeping everything in full precision RAM. Naming, approximate, and memory bound upfront is the senior tell. First, why can't you just use the Postgres or MySQL you already run? Because traditional databases are built for a completely different question. A B-tree index answers, find the row where id equals 42, or everything between Monday and Friday, exact matches and one-dimensional ranges. But an embedding is a point in a space with hundreds or thousands of dimensions, and the question isn't equals, it's what's closest. A B-tree is useless for that. There's no way to sort a 1,000-dimensional space along a single axis so that nearby points stay nearby. And here's the deeper reason it's genuinely hard. A thing called the curse of dimensionality. In high-dimensional space, Intuition breaks. Volume concentrates in the corners. Distances between points bunch up, and everything becomes roughly equidistant from everything else. The geometry that makes low-dimensional search easy simply stops working. So you need purpose-built index structures designed from scratch for approximate nearest neighbor in high dimensions. But, and this is the senior nuance to say out loud, this does not mean you always need a dedicated database like Pinecone or Qdrant. Postgres with the PG vector extension now does vector search inside the database you already operate. And for most products, up to a few million vectors, that is the correct starting point. One system to run, transactional consistency for free, joins with your real data. You reach for a dedicated vector database when scale or filtering or a strict latency target forces you to, not by default. Knowing that PG vector is the sane default, and when it stops being enough, is itself a strong signal. And be concrete about when it stops. PG vector is wonderful until your index no longer fits comfortably in your database's memory, or your write and query load starts competing with your transactional workload for the same CPU, or you need filtering and sharding features the extension doesn't do well. That's the moment you graduate to a dedicated system, not before. The trap in both directions is real. Juniors reach for a distributed vector cluster to store 50,000 embeddings, and other teams try to force 200 million vectors through an extension that's straining. The judgment is matching the tool to the actual scale. Let's ground the foundation, because everything rests on it. An embedding is a list of numbers, a vector, produced by a model that captures the meaning of a piece of content and positions it so that similar things sit close together in the space. Dog and puppy land near each other. Dog and tax return land far apart. The model does the hard part, turning text, images, or audio into geometry. And the database's job is narrow. Store those points, and, given a query point, find the nearest ones fast. Now, close needs a precise definition, a distance metric, and there are three you should know. Cosine similarity measures the angle between two vectors and ignores their length. It's the default for text, because meaning is about direction, not magnitude. Dot product, which folds in magnitude and is common when vectors are normalized. And Euclidean distance, straight line distance, when magnitude genuinely matters. The one thing you must get right. Your distance metric has to match how the embedding model was trained. Use cosine on a model trained for cosine. Mismatch it, and your similarity scores are quietly, subtly meaningless, and nothing will throw an error. And here's the punchline that reframes the whole interview. The quality ceiling of your entire system is set by your embedding model, not your database. A better embedding model helps far more than a fancier index. That's why the staff-level line is, the embedding model choice matters more than the database choice. The database only makes retrieval fast. It can't make a bad embedding mean something. Two things worth knowing that separate people who've shipped this. Dimensionality is a direct cost lever. A common text embedding is somewhere between 384 and 1536 dimensions, and every extra dimension is more bytes to store, more RAM, and more math per comparison. So bigger is not automatically better once you factor in cost and latency. And the frontier of representation, worth a sentence if it comes up. Instead of one vector per document, multi-vector or late interaction models like Colbert store one vector per token and match at the token level. Dramatically better retrieval quality at the cost of far more storage and a more complex index. Most systems don't need it, but naming that single vector per document is a simplification, not a law, shows real depth. So we have a query vector and 10 million stored vectors. Exact search, the flat index, compares against all of them and is guaranteed to return the true top k. Its cost is order n times d, number of vectors times dimensions. And say this out loud, because it's a maturity signal. At small scale, tens of thousands of vectors, a brute force flat index is correct, simple, and fast enough, and you should not over-engineer past it. But at 10 million, 100 million, a billion, that linear scan collapses under any real latency budget. So you switch to approximate nearest neighbor, ANN, and you accept a stated trade-off. You will occasionally miss a true neighbor, and in exchange, you scan a microscopic fraction of the data and answer in milliseconds. We measure the damage with recall. Of the true top 10 nearest, how many did you actually return? 95% recall means you found 9.5 of the true 10 on average. And for search, recommendations, or RAG, nobody notices the occasional slightly imperfect result. And now the frame for the rest of this video, the single mental model to draw. Every ANN approach is a point on a triangle. Recall, latency, and memory. You can be fast and accurate, but memory hungry. You can be memory cheap and accurate, but slower. You can be fast and cheap, but sloppy. You cannot maximize all three at once. HNSW, IVF, product quantization, DiskANN. Every one of them is just a different bet on that triangle. Keep the triangle in your head, and the entire field organizes itself. The most popular ANN index, and the one you must be able to draw, is HNSW, Hierarchical Navigable Small World. Build it in 2 steps. Step 1, a navigable small world graph. Connect every vector to its few nearest neighbors, forming a graph where you can walk from any point to any other in a handful of hops, like 6 degrees of separation. To search, you start somewhere and greedily walk toward the query, hopping to whichever neighbor is closer until you can't get closer. That finds near neighbors without checking everything, but on one giant flat graph, the walk is still too slow. So step 2, the clever part, hierarchy, and it's exactly a skip list made of graphs. You build layers. The bottom layer holds every vector, densely connected. The fine detail. Each layer above is a sparse sample of the one below, with long-range links, the highways. A search starts at the top. Sparsest layer takes a few giant hops to land in the right region fast, drops down a layer, refines, drops again, and finishes with precise local steps at the bottom. Coarse to fine. That hierarchy turns the walk from linear into roughly logarithmic. You find excellent neighbors while touching a vanishingly small fraction of the graph. 3 knobs to name. M. How many neighbors each node keeps. Bigger M, better recall, more memory. efConstruction. How hard you search while building the graph. And the one that matters live, efSearch. How many candidates you explore per query. Turn it up for more recall, down for less latency. That knob is the recall versus latency dial, in your hands at query time. Why logarithmic? Because each layer up has exponentially fewer nodes with longer links, so each descent roughly halves the region you're searching. The same reason a skip list turns a linked list scan into a logarithmic lookup. HNSW has the best recall to latency ratio in the business. So what's the catch? 2, and naming them unprompted is a staff signal. First, it is a memory hog. It doesn't just store your vectors, it stores an entire navigable graph on top. m links per node per layer. Picture 200 million vectors at 700 plus dimensions. That's hundreds of gigabytes of raw floats before a single graph edge, and to stay fast, the whole thing wants to live in RAM. At real scale, you're not paying for search. You're paying rent on a giant in-memory graph. That one fact is what forces every compression and disk trick in the next 3 chapters. Second, the catch almost nobody sees coming: deletes. How do you remove a vector from an HNSW graph? You'd have to find every node pointing at it and rewire them. And HNSW doesn't even store those reverse links, so a single delete becomes a localized rebuild that cascades, especially if you delete a hub, one of those long-range highway nodes that made search logarithmic in the first place. Rip out a highway and you don't lose one data point. You lose speed for everything routing through it. So production systems don't delete, they tombstone. Flip a deleted bit, leave the node in the graph as a routing waypoint, and filter it out of the results. The cost you must name. Tombstones accumulate, so you overfetch to compensate. Ask for 10, get 4 live and 6 dead. Latency creeps up, recall quietly degrades, and eventually you rebuild the whole index offline. Saying HNSW deletes are effectively a rebuild, so you tombstone and track the tombstone ratio as an SLO is genuinely senior. When your RAM bill triggers a budget review, you reach for the other big family, and it starts with a different idea. Instead of one giant graph, partition the space. This is IVF, the inverted file index. Run k-means clustering over your vectors to carve the space into, say, a few thousand cells, each with a centroid. Think of them as neighborhoods on a map, each with a town center. You store, for each cell, the list of vectors that fall inside it, an inverted list, hence the name. To search, you don't scan everything. You find the handful of centroids nearest your query, then only look inside those cells. A parameter called nprobe controls how many cells you probe. Probe more for higher recall and more latency. Probe fewer to go faster and risk missing a neighbor that sits just across a cell border. That border problem is IVF's characteristic weakness. A true nearest neighbor can live in an adjacent cell you didn't probe, so recall is usually a touch lower than HNSW at the same speed. What you buy in return is simplicity and memory. You're holding a routing table of centroids plus flat lists, not a dense multi-layer graph. 2 details that show depth. IVF has a training step. You run k-means on a representative sample before you can insert. So unlike HNSW, it isn't purely incremental, and if your data drifts, those centroids go stale and you retrain. And the cells are rarely balanced. Real embeddings clump, so some cells are huge and some nearly empty. On its own, IVF, where each cell holds full vectors, is called IVF flat, accurate but still memory heavy. The framing, HNSW, navigates a graph, IVF narrows to a neighborhood, and those flat lists inside each cell are exactly where compression pays off. Here's the lever that tames the memory wall and the vocabulary that impresses: quantization. Stop storing vectors at full precision. 3 levels, increasingly aggressive. Scalar quantization. Each number in the vector is a 32-bit float. Snap it to an 8-bit integer instead. That's a 4 times shrink for a tiny, often negligible recall hit. The cheap, safe first move most systems make by default. Product quantization, PQ, goes further, and it's the classic term. Chop each vector into small subvectors, and for each, learn a little codebook of representative values and store just the index of the closest one. A 3 kilobyte vector collapses to maybe 64 bytes, a 50 times reduction. And the aggressive frontier, increasingly common, binary quantization, reduce each dimension to a single bit. Is it positive or negative? And compare with Hamming distance, which is blindingly fast on a CPU. That's up to a 32 times shrink, with newer schemes making it far more accurate than it has any right to be. Now, the honest cost, stated plainly, quantization is lossy. You're searching approximations of your vectors, so recall drops, sometimes hard for binary. The universal fix is re-ranking. Use the tiny compressed codes for a fast, rough first pass to get a candidate list, then pull the full precision vectors for just those few candidates and rescore them exactly. Fast filter, accurate finish. One idea that impresses: asymmetric distance computation. You compare a full precision query against compressed stored vectors without decompressing them. By pre-computing a small table of distances to each codebook entry, so scoring a candidate is a few table lookups. Combine IVF with PQ, IVF-PQ, and a 600 gigabyte problem becomes a 15 gigabyte one that fits on a single machine. The framing: HNSW spends memory to buy speed. Quantization spends a little recall to buy back enormous memory, and re-ranking hides most of the loss. So far, every fast index has wanted to live in RAM, and RAM at billion vector scale is where budgets go to die. The modern answer, and a genuinely impressive thing to name, is DiskANN, built on a graph called Voronoi, which makes graph search disk native. Here's the elegant trick, and it stitches together everything we just covered. You keep 2 copies of your data. A tiny product quantized copy of every vector lives in RAM, small enough that a billion vectors fit in a modest amount of memory, and the full precision vectors plus the graph live on the SSD. The search walks the Voronoi graph, using the compressed vectors in RAM for its distance comparisons, cheap, fast, no disk hit for the navigation. And only when it has narrowed to the top handful of candidates does it do a few precise disk reads to fetch their full vectors and re-rank exactly. Same pattern as the last chapter: rough fast, then precise slow. But now the slow tier is an SSD instead of RAM. The payoff is dramatic. You serve a billion vector index from a single machine at high recall for something like 40 times cheaper than the all-in RAM HNSW equivalent, because SSD is orders of magnitude cheaper per gigabyte than DRAM. The cost you name, honestly, those disk reads add latency, and the whole game is read amplification. How many random disk reads per query? Voronoi's graph is deliberately built with longer range edges, so the walk reaches the answer in fewer hops, and each hop's neighbor list is laid out to be read in one-page fetch. The entire design is bent toward minimizing disk touches. DiskANN is why a billion vectors needs a fleet of huge memory machines stopped being true. You can do it on one box with a big SSD and modest RAM. Step back, because now the whole field snaps into a single picture. And this is the frame that makes you sound like you've operated these systems. Every technique we've covered is one rung on a memory ladder, and the ladder exists because of one pressure. The fast index wants to be in RAM, and RAM is the expensive corner of the triangle. Rung 1, the top. Everything in RAM, full precision. HNSW at its fastest, most accurate, most expensive. Too expensive. Rung 2, compress the vectors in RAM, scalar, then product, then binary quantization, trading a little recall to fit far more per gigabyte. Still too big. Rung 3, Push the data to SSD DiskANN, keeping only tiny compressed codes in memory and the bulk on disk. And rung 4, the modern cloud move. Push it to object storage and separate storage from compute. Keep the vectors in something like S3, spin compute up and down independently, and stop paying to keep idle machines warm, just to hold data. That last step, popularized by systems like Turbo Puffer and adopted across the industry, means storage scales independently of query load. Put rough numbers on it. Full precision RAM is single-digit milliseconds. Quantization cuts memory 4 to 50 times for a small recall hit at similar latency. DiskANN pushes cost down roughly 40 times at billion scale for maybe tens of milliseconds. And object storage is pennies per gigabyte, but adds hundreds of milliseconds on a cold read, which is why you cache the hot set. The framing: you climb down the ladder as scale and cost pressure grow, trading latency for cost at each rung, and knowing which rung a workload belongs on is the actual engineering judgment the interview is testing. And notice the beautiful thing about the ladder. The same two ideas recur at every rung. Approximate to go fast, then re-rank with something more precise to win accuracy back. Quantization approximates in RAM and re-ranks on full vectors. DiskANN approximates in RAM and re-ranks from disk. Object storage caches a hot approximation and fetches the cold truth on demand. It's one pattern applied at 4 different storage tiers. Here's a problem that sounds trivial and is quietly brutal. And interviewers love it because it separates the whiteboard from the warehouse. Real queries are almost never just find similar. They're find similar documents that this user is allowed to see, or published after January, or in the electronics category, in stock. You're combining a vector search with a metadata filter, and the two obvious approaches both fail. Post-filtering: do the vector search first, then drop the results that don't match the filter. The trap is that your top 100 nearest might all get filtered out, leaving you with 3 results, or nothing, and you're forced to massively overfetch and pray. Pre-filtering: find everything matching the filter first, then vector search only those. Correct in principle, but if the filter matches millions of rows, you're back to a slow scan, and worse, your beautiful HNSW graph was built over the whole dataset, and you can't just walk it while ignoring most of the nodes because the highways run through the filtered-out points. Cut them, and the graph fragments. So this is a genuinely hard, active engineering problem, and modern systems attack it with real cleverness. Filtered HNSW that checks the metadata predicate during the graph walk and skips non-matching nodes while still routing through them. And metadata-aware partitioning. The key insight to state is that the right strategy depends on the filter's selectivity. If the filter passes almost everything, post-filter. If it passes almost nothing, pre-filter, and brute force the tiny matching set. The hard middle is where filtered graph traversal earns its keep. The senior move is naming that filtered vector search is a first-class problem with real failure modes, not a where clause you bolt on at the end. Real systems aren't static indexes rebuilt once a night. Vectors arrive constantly, and this is where the "it's a database" part bites. The core tension: the fast graph indexes are expensive to modify in place, but users expect new data searchable within seconds. The standard answer borrows straight from the storage engine playbook: a log-structured merge design, an LSM tree. You don't touch the big immutable index on every write. Instead, new vectors land in a small, fresh, in-memory segment that's cheap to search. A query fans out across the big index and the little fresh segment, and merges the results, and in the background, segments are periodically merged and re-indexed into larger ones. Writes stay fast, data stays fresh, and the heavy indexing happens off the hot path. There's a consistency angle worth naming here too, because a query reads the big index plus one or more fresh segments. Systems usually give you a consistent snapshot per query, but only eventual visibility of a brand new write. That few-second lag you agreed to back in requirements is exactly what buys this architecture its speed. Deletes ride the tombstone mechanism from the HNSW chapter. Mark, filter from results, compact later. And the update everyone forgets, the one that's really a migration, embedding drift. The day you upgrade or change your embedding model, every stored vector is now in the wrong space. You cannot compare a vector from the old model against one from the new model. The geometry is different. So changing the model means re-embedding and re-indexing your entire corpus, a full backfill, often with a dual write or shadow period, so you don't take downtime. It's not a config flag, it's a data migration project. Naming embedding drift as a migration, unprompted, tells a senior interviewer you've actually lived through a model upgrade. Now push it past one machine, and the real system shape appears. And it's a distributed systems problem wearing an ANN hat. Sharding. A billion vectors won't fit on one node, so you split the index across many. But here's what's different from a normal database. Vector search does not shard cleanly. In a key-value store, you route a request to the one shard that owns the key. In vector search, you can't, because the nearest neighbors to a query could live on any shard. There's no key to route by. So every query scatters to all shards, each searches its own slice, and a coordinator gathers and merges the top candidates. Classic scatter-gather. The consequence you must state, your latency is bounded by the slowest shard, so tail latency and stragglers matter enormously at scale. And because every query hits every shard, adding shards does not reduce per query work the way it does in a key-value store. It buys capacity, not latency, and it makes tail latency worse. You generally shard randomly, not by content, because you want each shard to hold a representative slice of the whole space. Replication layers on top for throughput and availability. Copy each shard. So many queries run in parallel, and a dead node doesn't lose data. Then the modern architectural move, separate storage from compute. Keep vectors in cheap object storage, load them into stateless compute nodes on demand, and scale the two independently. So a huge but rarely queried dataset costs almost nothing to hold. The takeaway: at scale, a vector database is scatter-gather over sharded ANN indexes, replicated for availability increasingly with storage split from compute. The algorithm is the easy part. The distributed system around it is the job. Here's the refinement that separates a demo from a production retrieval system, and it ties this whole video back to RAG. Pure vector search is fantastic at meaning comfortable running shoes matches cushioned sneakers, even with no shared words, but it's oddly bad at exact matches, precise product codes, rare proper nouns, an exact error string. It might rank a semantically similar but wrong result above the document containing the literal code you searched for. The fix is hybrid search. Run a dense vector search and a classic sparse keyword search, BM25, the decades-old workhorse, in parallel, then fuse their rankings. The standard fusion method to name is reciprocal rank fusion, RRF, which combines the two ranked lists by rank position without needing their scores on the same scale, simple and robust. dense for meaning, sparse for exact terms, fused into one list. And then the final quality layer, borrowed from search, re-ranking with a cross encoder. Your ANN index is a fast by-encoder retriever. It embedded the query and documents separately, which is what makes it indexable. But that separation loses precision. So you retrieve a generous top 100 cheaply, then run a slower, far more accurate cross-encoder that reads the query and each candidate together and rescores them, keeping the top 10. Cheap wide net, expensive precise finish. Notice the recurring shape across this entire video. A fast approximate stage to narrow, then a slow exact stage to refine. Brute force re-rank after PQ. Disk reads after the RAM walk in DiskANN. A cross-encoder after the by-encoder here. That retrieve then re-rank pattern is the single most important idea in production retrieval. And it's why the ANN index only has to be good enough to get the right document into the top 100, not perfect. A quick tour of where this is going, because a strong candidate shows awareness of the frontier without getting lost in it. GPU-accelerated indexes. Building and searching these graphs is embarrassingly parallel, so NVIDIA's Kagra and the QUVS library now run index builds and queries on the GPU, with reported 4 to 20 times speedups over CPU, increasingly co-located with the LLM's own GPUs for RAG. Matryoshka embeddings, newer embedding models are trained so that the first few hundred dimensions already hold most of the meaning, like nested dolls, so you can truncate a vector, use the first 256 of 1500 dimensions, and trade a little accuracy for a big cut in memory and latency, tuning dimension count like any other knob. Binary quantization continues to push how cheap a good enough first pass can be, with re-ranking on full vectors clawing the recall back. There's also a whole family beyond HNSW, and DiskANN worth a nod. Span, for instance, is a partition-based index that keeps the centroids in memory and the posting lists on disk. Another point on the memory versus cost curve for billion-scale data. And tiered storage is becoming standard. Hot vectors in RAM, warm on SSD, cold in object storage, with the system promoting and demoting them by access pattern, the memory ladder made automatic. And the ecosystem itself has converged. As of 2026, Pinecone, Quadrant, Weaviate, Milvus, and PG Vector have reached rough feature parity. They all do HNSW, hybrid search, filtering, quantization, and disk or GPU options. So the real decision is no longer which has the features, but deployment model, operational overhead, and cost at your scale. That reframing, that the algorithms have commoditized and the operations are the differentiator, is exactly the kind of thing a staff engineer says, let's make this a decision you can defend. Because which index is the question you will get asked. Small data, tens of thousands, even low millions. Flat, exact search, and don't apologize for it. It's correct, simple, and the recall is a perfect 100%. Need the best recall to latency ratio, and you have the RAM to spend. HNSW, the workhorse default of most vector databases. Memory constrained but still want it in RAM. Add quantization, scalar first, then IVFPQ when you need aggressive compression. Billion scale and cost matters more than raw latency, DiskANN on SSD, or push to object storage with separated compute for cold, bursty data. And for most products under a few million vectors, the honest answer is still PG vector inside the Postgres you already run. Two more principles to state. First, recall is a dial, not a fixed property. efSearch in HNSW, nprobe in IVF. So you measure recall against a ground truth set and turn the knob until you hit your latency target. And how do you get that ground truth? Take a sample of real queries, compute their true nearest neighbors once with slow, exact brute force, then check what fraction your index recovers, sweeping the knobs to plot recall against latency. Second, pick the index to fit the workload and the budget, not your favorite paper. Saying it depends on scale, recall target, and cost. And here's the decision tree, and I'd verify it against a ground truth set, is the answer. Naming one product as the universal solution is the red flag, the traps that sink the interview. 1. Proposing a brute force scan at scale. Order n dies, you need ANN. Not knowing that is disqualifying. 2. Not knowing vector search is approximate. That's the entire point of the category, and missing it means you've never really used one. 3. Naming pinecone with no idea how the index works. You must be able to explain HNSW or IVF. 4. Ignoring the recall latency memory triangle. Every choice is a point on it, and pretending you can have all three is naive. 5. Forgetting HNSW is a memory hog. It's what forces quantization and DiskANN. 6. Thinking deletes are cheap. They're effectively a rebuild, tombstone. 7. Treating filtered search as a trivial where clause. Pre- and post-filter each have a real failure mode. 8. Mismatching the distance metric to the embedding model. Silent, meaningless scores. 9. Forgetting to re-embed when the model changes. A stale index of the wrong space. 10. Reaching for a dedicated cluster when pgvector would do. Over-engineering the default. The flip side of under-engineering at scale. And 11. Quoting a recall number you never measured. Recall is a property of your data and your knobs, so if you can't say how you'd build a ground truth set and tune against it, you're guessing. Hit a handful of these, and the interviewer knows it's book knowledge, not scars. So, a vector database trades a perfect answer for a fast one. It is approximate by design, and the whole field is one triangle. Recall, latency, and memory, with memory usually the binding corner. Brute force is order n, and dies at scale, so you use ANN, and you measure it as recall. HNSW is a skip list of navigable graphs, coarse to fine, the best recall to latency ratio, but a memory hog whose deletes are rebuilds, so you tombstone. IVF partitions the space into cells you probe. Quantization, scalar, product, binary, shrinks the vectors from kilobytes to bytes, and you re-rank with full precision to win back recall. DiskANN puts the graph on SSD with tiny compressed codes in RAM, serving a billion vectors on one box for a fraction of the cost. One rung on the memory ladder from RAM to compressed to SSD to object storage with compute split off. Treat filtered search as a genuinely hard, first-class problem. Keep data fresh with LSM-style segments. And remember that changing your embedding model is a full re-indexing migration. At scale, it's scatter-gather over shards, and real retrieval adds hybrid dense plus sparse search and a cross-encoder re-ranker. Match your metric to your model. Remember, the embedding model matters more than the database, and start with pgvector until scale forces you down the ladder. Get that, and you understand the engine under every RAG system, every recommender, every find similar on the internet, and you can defend the trade at every layer. This is exactly where machine learning meets real system design, and it's what the top companies are testing right now. Practice this exact interview with an AI interviewer that pushes back, free at crackit.io. Design the system, then go defend it. See you in the next one.